In this example, I'd like to address one of the most underused aspects in simulations as well as Houdini as a whole, and that's time. We are so focused on the 3D surface and the geometry that we often fail to look at how we can use time more efficiently in our setups. And in this example, I want to call this thinking like an animator in dynamics because some of the most successful dynamics TDs I've seen and worked with have been really, really good animators. It's one thing to have the technical background, it's very important. It's important to know how to set up the constraints and some scripting, but really to think about the effect as an animation can really get certain effects very far and save tons and tons of simulation time. So in this example I put together, we're going to use a simulation in a bit more abstract way. I ran across a student a few years ago, and he was doing spikes coming out of the ground, and helped him through that setup. And it turned out that a spike going full speed through the ground would send these pieces flying, and there's just no way to control the effect because one of the most crucial aspects of a dynamic simulation is the impact. And normally in a high speed impact, you only really have 1 or 2 frames to work with. It's just not enough dynamics time based resolution in order to really get more of a representation of what would happen. So, rethinking that effect, I think that one of the crucial things to do in these kind of circumstances is to maybe think about time in a little bit more abstract way. So, here I'm just doing one simulation for each spike. It's the same simulation for this spike versus this spike. And we're going to copy this simulation, but change the timing of the simulation according to an arbitrary number of spikes and an arbitrary impact time. What might seem like very aggressive spike impacts is actually a really, really mild, very, very slow impact. And we're just using dynamics more for the actual deformation of all this ground here. Okay, so moving over to the right-hand side, I've just got these gray nodes over here, and this is going to serve as our starting point because we've already gone through several things in other lessons that address fracturing and setting up collisions. Okay, so here's a fractured ground based on this spike. And it's packed right now. If you want to change the density, you can change the density and then hit stash input here. Okay, so the first thing I want to try to do is I just want to set up a little test bed for the actual dynamic simulation. It's going to be a very slow moving spike going through this ground. So I want a collider on each side as well as one in the ground. So I'm going to start off using a box. Okay, so there's our bounding box. And I'm going to sort the polygons by Y so we can isolate the top and the bottom polygons. So polygons, primitive sort by Y. And then we'll use the blast. We know that a polygon has, a box has 6 primitives, so we'll delete 0 and 5. Now we have some 4 boxes ready to go here. We'll do a facet for unique points, and then a poly extrude to extrude locally. And now we have a really good set of colliders for static geometry to hold that in place. And now we need something on the bottom to keep it from falling through the ground. So we need another box perhaps. And with the transform, just going to subtract its own y maximum. So y minimum minus y maximum. Okay, and now we've got something on the resting on the bottom here too. So merging these together. So I'm just going to collapse that whole thing and call that ground. And one thing I should probably mention is that we want to make sure there's no non-watertight surfaces. So that's in my poly extrude. I forgot to do output back. Okay, so always check for that. And now we want to set a few keyframes. And the thought of keyframes seems like a very non-procedural, maybe a scary prospect. But in this circumstance, we're doing something that's so simple that actually keyframes are the most straightforward way to go about it. So here, I just want the spike going slowly from the bottom upwards. So we're going to subtract its y maximum. Okay, so now it's basically starting on the bottom. And I'm just going to animate this transform going from bottom to top. So we're going to set a keyframe on Y of a transform. And I'm just going to be very exacting about this. I just want a very controlled scenario. So going to frame 100 so I know exactly how long it is. And let's just raise this second keyframe almost to the top there. And we don't need any ease in or ease out. So if yours defaults to that, like mine did, I'm just going to set these to linear. Okay, so now we've got this very controlled spike raising off the ground, and we've got a nice little set of things to keep the pieces from falling. Okay, so the first part about thinking about it like things like an animator is being able to use this transform for something, use the animation we just did for something, having objects that are external to the simulation affect the simulation. Okay, so the best way to do that is to use the transform directly. We don't really want deforming geometry in the sim. It's slow and it's very error prone. We have to recalculate collisions on every frame. So instead, we're going to use the extract transform. Okay, and here we're going to post-compute the transform of this cone. So we need a reference geometry, so we can use a time shift for that. We just want to log off the time. It's best downstream. So I'm going to put that to the start. Okay, so there's our starting point. And the transform will be the moving one. And because the topology is not changing and our object is not deforming, we've got this nice little transformation happening now. Okay, that's the transform. Okay, so that's all we need to do to set up the initial basis of our simulation. We've got a ground, we've got a point that's transforming, we've got some actual transform geometry, which is this guy, and we've got some fractured stuff. All right, so let's set up a new DOPS network. Okay, so I'm going to put the static ground collider, I'm going to put the fractured geometry, and I'm going to put this moving point in here, the fourth input, and I'm going to put the reference geometry, the spike, in the third input. So let's start by setting up our static and animated colliders. So start off with a RBD object. Okay, so this is just reading from the first input. And I'll call this ground. Okay, now by default, these collisions are not going to be very good. Looking over at bullet data, you see we've just got a convex collision mesh. So I'm going to say create convex hull. And now that's great. Okay. Now we want the animated collider. That's a little more tricky. So with another RBD object, I'm going to change this to 1. I'm going to call this spike. Actually, change it to 2. Okay, our reference geometry. Okay, for the spike. And with this object, I want this to be transforming, not deforming. I do not want to activate use deforming geometry, because what that's going to do is it's going to cause things to recalculate on every frame. I just want to calculate this object once and then move it, and then we get nice collisions, nice velocities. So we're going to use the point position DOP in order to do that. The only caveat here is we have to set this to read from the current time, $T, and set always. And for the SOP path, that's going to be backticks op input path, the fourth input, which is index 3. So if that works, now we've got a transforming object. Okay, we can see down here in position that these numbers should be moving. The object itself, the points are not deforming. These numbers are moving though. And now let's merge in the fracture geometry. So I'm going to do a packed object. And that would be, I believe, the second context. There we go. And let's merge all that together. Okay, so the ground merge with the spike. And then on the ground chunks, we want some gravity. Here we don't really need constraints. We want a rigid body solver. And then another merge. And let's see what that does. Okay, very fast, very efficient, and most importantly, controlled. There's not a whole lot that can go wrong in a simulation like this, and we can make these pieces pretty much as dense as we'd like, as long as we're willing to wait for one simulation to cook, and it will give us the desired result of a spike poking through the ground. For that explosive look, then you can always trigger particle hits and things like that after, or even use these velocities in another simulation afterwards. But here, it's very controlled over about 100 frames, and I'm going to say that this entire effect, this animation, is going to last a total of 200 frames. And there we have that. And that 200 frames should give this enough time to settle. Okay, so there's our animation. It's a simulation, but we're going to treat it like an animation. Starting with 5 points, let's make 5 spikes come out of the ground and trigger this animation. So one of the whole things that I found working with procedural animation is you can almost always guarantee there's going to be an attack time and a duration. So I want these spikes to be animated coming out of the ground anywhere from a certain start frame to a certain end frame, and then have a variation in the durations. So diving in here, I'm just going to generate some random start times. So I'm using the point number and an offset for the seed, and we can fit that to our start frame and end frame. And then we also need some durations. So I'm going to make another seed, another fit, and then we'll assign durations to that. We'll call this minimum duration. And maximum duration. Okay, so I'm going to save this as frame. Invisible when input is connected. Okay, so exporting that as the frame attribute. We've got that. And then here we can export duration. Okay. Okay, so we've got a seed here. We've got, when should our animations start? I'm going to start them around frame 15. And they're going to continue until perhaps as late as frame 40. And then for the duration, I want these things to last anywhere from 15 frames to 30 frames. For now, half a second to a second. So far this is pretty straightforward. Just 2 random numbers along a certain range. And now I want to convert these 2 numbers into an actual frame-based lookup. So I'm going to separate that into a different step here in case you want to use it for other things too. So this will be our frame and duration, and this will be our frame lookup. And let's just read in these two attributes. Okay, so in comes the frame, and we want to make a lookup out of this. So here we would fit the current frame coming in, and we know the minimum frame it could be is the start frame. So a minimum is going to be the start frame. The maximum it could ever be is going to be the frame plus the duration, and that's the maximum. And then it's going to be, of course, going to 0 to 1, and that'll give us a lookup. And if we wanted to give that some dramatic emphasis, some emphasis on the timing, which is very much an animation thing that we want to do, we could use a ramp, similar to how you'd give some emphasis, some ease in or ease out, or some emphasis. Okay, so we'll call this lookup curve. Let's make that a spline ramp. So 0 to 1 coming in. Now let's fit this to an actual frame range. So I'm going to follow this up with these 0 to 1 values coming out of here, up with a fit. And we want this to be the start of our simulation. So we can call this maybe sim start frame and sim end frame. There we go. And let's export that as, call it lookup frame maybe, or sim frame. Okay, there we go. All right, so the start of our simulation is 1, and the end of our simulation is frame 200. And it's just going to progress linearly right now, but we can give that some emphasis. So these spikes would probably go from slow to fast and then kind of teeter off at the end. So it'd be something that looked a little bit like this, and then just a little bit of slowdown at the end for starters. Okay, so we've got these attributes, and now you can see how as I scrub the timeline, we've created a time dependency here by adding in the frame. So that's happening really fast. It's not taking 200 frames to do that. Okay, so let's import our animation now. So if we just wanted to copy over these spikes, so here's the animated spike. So we could do a copy to points, and in comes the spike, and in comes that. Okay, so they're all doing the same thing right now. So how do we make these frames here respect this lookup frame? Well, we could put this inside of a for each, and then we could reference each individual point and have it grab a different time at just before it gets copied. So I'm going to do a for each point. Okay, so for each points, and here it should gather just 1 point. That guy's going to be going into here. And now I'm going to do a time shift right here. So this time shift will just get the value of whatever this lookup frame is. So I'm going to do a point expression. Point for each begin 1. We want 0.0 because there's only 1 point. We're going to do lookup frame and the 0th index. Okay, so if we loop through and do that for each, and we could probably turn off integer frames because it's an animation here, but we want integer frames for the simulation. So it's just going to grab the closest integer frame. Now we're actually offsetting the time differently for each of these spikes. Okay, so it won't take much more effort to do the same exact thing with this simulation, because the simulation is operating at the same exact time as these spikes are. So we need to get it out of the simulation very efficiently. So instead of just merging the geometry, we're going to use a DOP import and merge a point cloud with the transforms present. So we can say create points to represent objects. So this can be cached out. This is a lightning fast representation of the only really important information contained in the simulation, which is the transforms. And they have orient attributes and positions, velocities, everything we need to retransform our pieces. So if we were to use a transform pieces And these are going to be our transforms, template points. Our pieces are going to be the rendering geometry, which I put into the second input here. And now we should get in the original representation of these pieces here. Looks like it's working good. And I'll also note that this is a really great stage to cache out your simulation right here. You only need to cache out the rest render geometry and the sim to rebuild the simulation in a really lightweight disk sort of way. So I'm just going to go ahead and copy this cache node that I've made. And let's just cache out the result of this DOP import. Save to disk. And I'm just caching out frames 1 to 200. Okay, so now that we have an efficient playback mechanism, it's all cached out, we can really be as creative as we want with this. So I'm just going to go ahead and merge that together with our spike. And now what do we get? Okay, so now we're retiming the animations according to when the spikes happen. If we wanted a little bit of rotational variation, we could do one more thing here, which is to give a random directionality to our copy. So I'm going to go ahead and add one more point VOP, a random seed. Okay, so point number, new offset. Here's our random vector. If we put that into the normal, we get random vectors. And I'm just going to use the flatten on axis digital asset that I've made, and I just want to flatten that on the y-axis. Okay, so here's our vector, and let's flatten that on the y-axis, and then using that, now we just have some random rotations in here, and that gives it a little bit more variation. Okay, so thinking like an animator, we were able to turn a fairly intensive setup even for 5 pieces, and it could be a host to lots of simulation issues as these things really break through at high velocities. And now, if this is the needs of the scene, now we can trigger particle effects, now we can do secondary sims, and we can have the base of our sim working just fine. Here I'm going to make the grid a lot bigger, just to show how scalable this system is. Okay, so lots of these cones happening at different times, and we really only had to do one simulation, and we can work on the granular detail of that one simulation. Here's a flipbook of the result of all of our spikes. And with the number of pieces and all of these different timings and all of the variability that could happen, if we didn't approach this like an animator, this could be potentially a show-stopping simulation just for a little bit of tearing and deformation on the ground. From here, we can do secondary, much lighter weight simulations like triggering particle effects or other rigid body simulations off of these pieces and off of what's happening. But the basic look can be established with just one simulation and working with time directly.